So, you have encountered cyclopentadienyl complexes already when we've insisted on putting them in order to allow us to have slightly more ambitious electron counting exercises. This lecture is dedicated to complexes of the cyclopentadienyl ligand in their own right. The history of cyclopentadienyl complexes is a very interesting one because Miller and Powson found that when they were working with cyclopentadiene, was that what they got out were beautiful orange crystals. And meanwhile, Powson was actually looking at trying to oxidize not cyclopentadiene, but in this case the Grignard reagent of cyclopentadienyl magnesium bromide with iron trichloride, and he got exactly the same product. So we have two completely different routes leading to exactly the same chemical product. And this was no ordinary organic product. This was beautiful orange crystals that could sublime, that were really very stable, and as we'll see in a little while, you could do subsequent chemistry with. So there was some very interesting compound coming out. Now, being organic chemists, they said, well, what is the bonding here? We've clearly got an iron complex. How might the iron complex be bonded to our cyclopentadienyl species? And quite reasonably, for organic chemists working in the early 1950s, they proposed a structure like this, where we have sigma-bonded cyclopentadienyl ligands. So we know that these sigma-bonded cyclopentadienyl ligands would be 1 electron donors to the iron. And so if we do a quick electron count, then you and I will recognize immediately that this species would be a 10 electron compound. And as a 10 electron compound, we would not predict it to be very stable. But this is the 1950s. These are organic chemists. They weren't concerned with concepts like this. Organometallic chemists working at the same time included Geoffrey Wilkinson and Ernst Otto Fischer, and their insight was that perhaps it's not an eta-1 coordination of the cyclopentadienyl ligand. Perhaps those double bond functionalities are also involved in bonding to the transition metal. And if you draw those species as interacting with the transition metal, then you get a representation like this, which we'll recognize immediately would have a number of equivalent resonance canonical forms. And so we would draw this as being a delocalized species here. And so Wilkinson called these compounds sandwich compounds. Fischer called them double cones. But what they were describing was exactly the same thing. An iron atom sandwiched or at the apex of two cones between two cyclopentadienyl ligands. And of course, if these cyclopentadienyl ligands are now eta5, we have an 18 electron complex. So now you, knowing what you know about the 18 electron rule, would have predicted straight away that those alkene functions, knowing what you know about allyl ligands, you would have predicted straight away that those alkene functions were going to coordinate. Because if we think about a cyclopentadienyl ligand, we were talking about alkyls. So we had a metal, and then next to the metal we had a double bond. So in that case, you've got a sigma ligand and potentially a ligand capable of donating a pair of electrons here. And that would form a system that was delocalized like this and a 3 electron donor. So that's what we did on Monday. Now, if you take this species here and introduce another double bond here, and then actually join these up, so obviously what you've done then is you simply added another double bond to an allyl ligand. And so a cyclopentadienyl ligand is just one step beyond, or one double bond beyond, an allyl ligand, and just happens to be a cyclic fashion. There is a pentadienyl ligand, which is an open ligand. So it's perfectly possible to have a pentadienyl ligand which really is an alkyl conjugated with two alkenes and is not a closed species. But complexes of the pentadienyl ligand, although they exist, are nothing like as common as complexes of the cyclopentadienyl ligand. Now, like any good chemist, when you discover something new, you run with it. You throw the cyclopentadienyl ligand at every metal in the periodic table, largely. And that's what the groups of Wilkinson and Fischer and certain other people did. And very quickly, there's an explosion of cyclopentadienyl metal chemistry. And lots of different derivatives of these done. But the iron one was the first one. and it is by far the most important for reasons that we'll come on to in a slide or two. So we have cyclopentadienyl complexes. This compound here is called ferrocene. Now, why call it ferrocene? Why add this suffix "cene" on the end of it? The reason for that is because the chemistry of ferrocene resembles the chemistry of benzene. It behaves, chemically speaking, very much like it was an arene. So you know you can do electrophilic substitution reactions on benzene rings. You can do electrophilic substitution reactions on ferrocene molecules. So this is a Friedel-Crafts acylation reaction. You will have encountered one of those before. This time the reaction is actually on ferrocene. And if we think about it, in ferrocene you have a 5-membered ring here, which you can draw a formal negative charge on. So this 5-membered ring here is much more electron-rich than benzene. Because this is more electron-rich than benzene, it will undergo electrophilic substitution reactions much faster than benzene. So this does electrophilic substitution just like benzene, only about 1 million times faster. So ferrocene is much more reactive towards these reactions because it is a more electron-rich system. Okay, so we've already mentioned we have a whole huge explosion of these metallocene-like molecules. So ferrocene is the iron-containing compound. We just change that prefix in there if we're reflecting different metals, and they all become metallocenes. Now, occasionally there is a little bit of confusion about what is cyclopentadiene, what is a cyclopentadienyl ligand, what is a cyclopentadienide anion. So cyclopentadiene is CPH, not CP, CPH. CP is our radical 5-electron donor ligand. So CPH is this species here, where there are still 2 protons on that carbon atom. That is CPH. Don't abbreviate this to CP, that's not correct. It's protonated, it's not. So CP, or you might want to call it CP dot, is the sort of species we're considering when we're doing covalent electron counting. So when we're doing covalent electron counting, we have a species that looks like this. Now this makes no sense unless it's coordinated to a metal, but it's that bit we're referring to, a 5-electron system, if we're referring to just CP. CP minus, if you take cyclopentadiene and you react it with a very strong base of a metal that will not undergo pi-type interactions, for example, potassium hydride, then what you produce is a cyclopentadienide, and I'm being very careful with my language, anion. And this, of course, we can draw with various resonance forms and is equivalent to this species, which actually bears a negative charge. So when you're talking about the names of these compounds, you have to be very careful. This is CPH, cyclopentadiene. This is CP, the cyclopentadienyl radical. And this is CP minus, the cyclopentadienide anion species. Now, the cyclopentadienide anion is an ionic compound, or an anion, and it will have 6 pi electrons. You've got 2 double bonds here, 2 electrons each, and a pair of electrons here. So this is a 6 pi Huckel aromatic system. So when you're doing oxidation states, as we'll do later in the course, if you break the metal cyclopentadienyl ligand bond heterolytically to generate ions, then you generate a metal cation and you generate a cyclopentadienide anion. But of course, when we're doing covalent electron counting, we don't break the bonds heterolytically, we break them homolytically, and then you will generate, hypothetically speaking, a cyclopentadienyl radical and a metal-based radical. So there's no contradiction here. What we have in this system is essentially a conjugated unsaturated hydrocarbon. So I drew this as being like an alkyl ligand in conjugation with 2 alkenes. So what that means is it will bond like an alkyl ligand in conjugation with 2 alkenes. And so you will have sigma donor properties, you will have pi donor properties, by which I mean you are donating pi electrons, and you will have pi acceptor properties, by which we mean that the metal is donating electron density to the cyclopentadienyl anti-bonding orbital system. So it bonds in exactly the same way as an alkene. Is it easy to draw a simple orbital overlap diagram? No, because we're talking about many orbitals acting in concert on the metal and the ligand. But in principle, the donor and acceptor combination is the same as that on the alkene. You're just dealing with more orbitals at the same time. Now, if you actually look at the charge distribution, so when you're assigning oxidation states, you have to break the bonds. And so you consider then, you think, well, I'm going to make an anion and I'm going to make a cation. But that does not reflect the real charge distribution. So if we go back and we look at a ferrocene molecule, like this one here, this ring, each carbon in this ring, only bears a very small delta negative charge. The charge on the carbons on this ring is nothing like, adds up to nothing like -1. So that means is the electrons really are shared between the ligand and the metal. And if the electrons really are shared between the ligand and the metal, then our covalent bonding model is a much more appropriate bonding model than an ionic one would be. So it's appropriate to regard these compounds as covalent compounds rather than ionic. So what we have here is a look forward to when we really do need to bring oxidation states back into organometallic chemistry. And so if you wanted to assign an oxidation state to iron here, what you would have to do is you would have to break this bond heterolytically. And you break that bond heterolytically to make a cyclopentadienyl anion and an iron cation, and of course it would become an iron dication. And for that reason, we would say that the oxidation state, the formal oxidation state of iron, is iron 2. But, as I've just said, that does not mean that that really reflects the electron distribution in the actual molecule if you were to measure it. And it's for that reason, amongst others, that people like myself, Professor Botman, fortunately Dr. Redshaw, and all the organometallic chemists at UEA actually prefer this covalent electron counting convention. Is there anybody here who's got Shriver and Atkins, the textbook? No one? Okay, one or two of you have. Shriver and Atkins and the authors of that textbook use, by preference, a different counting convention. That counting convention works perfectly well if you stick to it regularly, but I'm not going to say any more just to acknowledge that there is an alternative way of counting electrons. The danger with it is that if I teach you this method and you try and learn that one, there's a potential for being confused. So what I say on this lecture course is separate electron counting, which you've all been doing brilliantly, from oxidation states, which I know you can also do brilliantly because Dr. Claydon taught you to do them so well, and you knew how to do that in the first year as well. So separate the concepts of oxidation state and electron counting and use the methods that you've been taught. What do we do if we're going to electron count ferrocene? Well, I bet everybody could have done this one already. What we have here is that iron is D8, like it's been in every one of the complexes we've encountered so far. Cp is a 5-electron donor, and therefore that's an 18-electron compound. How do you make these compounds? Well, everybody here by now has done topic 3 on the practical session, the synthesis of a cyclopentadienyl ruthenium compound. And you, whether you realised it or not, took some cyclopentadiene, which is this species here, from the still setup. And why was it necessary to take it from the still? Because this is a diene, and I'm sure you're all familiar with the Diels-Alder reaction. So not only is this a diene, it's actually a dienophile as well, and it very readily undergoes Diels-Alder dimerization to make this molecule, which is dicyclopentadiene. But that's a reversible reaction, and we can crack dicyclopentadiene to make 2 molecules of cyclopentadiene, which you can then go on and deprotonate with a base or whatever other kind of reactivity you have in mind. Best way to handle this for most transition metal chemistry, and this is yet another example of a metathesis route to an organometallic compound. So if we deprotonate our cyclopentadiene either using sodium metal or sodium hydride, then you will generate hydrogen, in both of those cases, although think about what the stoichiometry would be. It's different in both cases. So we generate a cyclopentadienyl salt with sodium cations. If you react that with a metal dichloride, that's how you make a metallocene. So that will work with a whole range of different metals. It will work with vanadium, chromium, manganese, iron, cobalt. All of those metallocene compounds can be made very easily just by taking the metal dichloride and 2 equivalents of sodium Cp. You can do something similar with nickel. If you start with nickel acac and use the cyclopentadienyl Grignard reagent, in that case you can make bis-Cp nickel. But bis-Cp nickel is not like ferrocene, as we'll see in a moment, and you can probably guess why it's not going to be as straightforward as ferrocene. So here we have a table, and I don't expect you to memorize all the details on this table. There are some very interesting points on this table. First of all, what we have here are the metallocenes. And what I've done, and I don't know how well it comes out on your handout, of course I've color-coded this slide, which doesn't work in black and white, I appreciate. But what we have here is bis-cyclopentadienyl vanadium, that is vanadocene, chromocene, manganocene, ferrocene, cobaltocene, and nickelocene. They're all different colours. And they all have different numbers of unpaired electrons, and therefore they exhibit different values for their magnetic moments. They're not all diamagnetic. Iron, ferrocene, is diamagnetic, but the rest of them have unpaired electrons and they're not diamagnetic. But look at this. Despite the fact they're all different colours with different numbers of unpaired electrons, they all have almost the same melting point. Different compounds, different masses, different numbers of unpaired electrons, but the same melting point. The melting point, of course, is related to the intermolecular forces between the molecules. It doesn't tell us anything about the strength of the bond between the metal and the cyclopentadienyl. It tells us about the strength of the forces between these molecules. And since they all seem to be the same, the most obvious conclusion to draw from that is that the structure of all of these metallocenes is the same. They all have the same shape, the same intermolecular packing going on. And that's true. The crystal structures have been determined, and these metallocene structure, this sandwich-like structure, is incredibly stable. So most of the time in organometallic chemistry, we've been looking at the 18-electron rule and saying we can predict which compound is going to be stable, how stable it is, based on the 18-electron rule. And what we've got here are compounds that are not obeying the 18-electron rule. And yet there they are, isolable compounds, some of them with odd numbers of electrons. So there really is something very special about the metallocene structure. The metallocene structure is imbuing special stability to these compounds. Now, it's no coincidence that the most stable of the metallocenes is ferrocene, which also happens to have 18 electrons. So where these two driving forces for stability coincide in ferrocene, then you have a particularly stable molecule. So if you can have a metallocene and an 18-electron compound, then you really are on to an organometallic winner. A compound so stable that you can start to do reactions on it just like it was an organic molecule like benzene. You cannot treat vanadocene or nickelocene through an attempt to do electrophilic substitution reactions. Those two molecules are not anything like as stable as ferrocene and won't work in that fashion. Okay, well, just a quick MO diagram here. Essentially, this MO diagram is the MO diagram for making a metallocene, and you can see here that we don't have the same separation in orbitals that we observe in those octahedral carbonyl compounds. And so this block here, it becomes possible to fill essentially all of this block here, and that's the explanation for why there isn't this huge driving force for an 18-electron compound. Right, vanadocene. Vanadocene is isolable. You can make it, you can put it in a bottle, but it's highly reactive. Vanadocene is a how many electron complex? It's a 15-electron complex. So you can see that vanadocene is going to be very easily reduced It wants to gain additional electrons to approach an 18 electron count. So this molecule's reactivity will be driven by a driving force of trying to get up to 18 electrons, of gaining additional electrons. Now, manganesine, bis-cyclopentadienyl manganese, is the one that bucks the trend a little bit, because at room temperature, bis-cyclopentadienyl manganese does not adopt a sandwich structure. It adopts a rather strange polymeric structure with bridging cyclopentadienyl groups. However, if you heat it to 158 degrees centigrade, it undergoes a phase change, and it does adopt a sandwich-like structure. So between 158 and about 174 degrees, manganesine is a sandwich compound. The most stable of them all, ferrocene. No coincidence, because it's an 18 electron compound. If you go to cobaltocene, you will have a 19 electron compound. And as a 19 electron compound, that species is going to be very favourable for it to lose an electron. If a species have a strong driving force to lose an electron, it will react as a what? If this compound, it's facile for this compound to lose an electron and become a cation, it gives up an electron, and as it has a tendency to give up an electron, it will be a reducing agent. So cobaltocene is a fairly powerful reducing agent because it's so favourable for it to lose an electron, become a cobaltocenium cation, and have an 18 electron count. Now, nicolocene is a very rare example, because what we have in nicolocene is a 20 electron species, a 20 electron organometallic species. That fact that it is a 20 electron organometallic species means that there tends to be a driving force for it to lose one of these cyclopentadienyl ligands, because only by actually losing one of the cyclopentadienyl ligands can we get down to an 18 electron count. So this is quite a reactive molecule. This one tends to just give up an electron and stay a metallocenium cation. This one has to actually lose one of the cyclopentadienyl ligands in its chemistry. Right. What's that? We seem to have a strange creature here, an interesting looking picture here. Now, okay, let's have a look at these. Ultimately, I'm going to ask you what all of these images have in common. But let's see if we can decipher what those images are before we do that, shall we? This is a what? It's a teddy bear. Okay, it's a teddy bear. This is a house. This is a... You're very generous. It is indeed Abigel. Well done, that person. Okay, so this is Abigel, my 5-year-old, and this is a metallocene. Right. So the question is, what do all these 5 objects have in common? They were all drawn by me, yes, by writing. You know by now that my artistic talents are somewhere less than non-existent. So, what do those 5 images have in common? And actually, Abigel is 5 now, and some people earlier saw her beating me at Wii Sports Resort Duel. Really, they did. So, what you have to ask now is what... 2 years ago, we were drawing these. So she was 3. So what do all these images have in common? Well, I have to tell you, they could all be named and recognised by a 3-year-old. All of these images could be named and recognised by a 3-year-old. So what is the point of that? Well, I would argue that if my 3-year-old knows that this is a metallocene, that after having been told that, you will never forget that this is a metallocene. Okay. How are we doing for time? Actually, we're not doing too badly for time. So on that note, to liven things up and get back into the sports, because the tests, you might be thinking, well, I haven't had any. This is because of the metallocenes. The metallocenes don't obey the 18 electron rule rigorously. We'll get to some compounds that do in a moment. But what I'd like to do now is just to show you a clip So hopefully everybody saw the Abigel band playing us in with the Sports Resort theme. Right, so you might be forgiven for thinking that you were never going to see another main group organometallic compound. Not true. You can make metallocenes of the main group elements, certainly the heavier elements of group 14, tin and lead make metallocenes. Now what you should remember from your tin and lead chemistry is that as you go down group 14 and indeed 13 and 15 as well, there's something called the inert pair effect. And the inert pair effect means that instead of being tetravalent, these molecules or these atoms behave like they're divalent. And that's what happens in this metallocene chemistry. But of course there's still a lone pair, an inert pair of electrons, and these are main group elements. So that inert pair of electrons is stereochemically active. So you can make a metallocene, but the metallocene will be bent. And it will be bent because it's being repelled by the lone pair, inert pair of electrons on the stanocene and plumocene, as they would be called. Not all main group molecules form what we would call metallocenes. And by metallocenes, of course, they have an element of a sandwich type arrangement to them. Bis-cyclopentadienyl mercury is an eta-1 bonded compound. So you remember the original supposition for the structure of ferrocene was an eta-1 bonded compound. Bis-cyclopentadienyl mercury really has that structure, but it doesn't mean that it's not dynamic. You can still race around here bonding to different positions on the ring. So it's strictly eta-1 bonded, but you can have an exchange between the different carbon positions in here. Now, bent metallocenes, what do we mean by bent metallocenes? Well, strictly, of course, the stanocene and plumocene are bent. They are bent because of the presence of a lone pair of electrons. If we go back to transition metal chemistry, in order to bend our metallocenes, there must be another ligand present. And of course, not all transition metals do their chemistry predominantly in oxidation state 2. If you look at titanium and vanadium, you normally have higher oxidation states. So if you start off with the metal tetrachloride and react that with 2 equivalents of sodium cyclopentadienyl, then you get elimination of 2 equivalents of sodium chloride, and you make what I would call a bent transition metal metallocene. Now, what I would note here is there are 2 possibilities for which metal the red blob might be. And you do need to use your organometallic acumen to work out what they might be. I will tell you it is the second row transition metal rather than the third row transition metal I'm looking on the slide. So I'll give you that additional piece of information. That doesn't answer the whole question, but it does help you to distinguish between the possibilities. So we have an example of an 18 electron second row metallocene there for you. Now, these bent metallocene compounds, they're really very important. They do an enormous amount of chemistry. The group 4 bent metallocenes in particular are extremely important reagents because derivatives of those are used in a number of synthetic processes. There are, for example, the TEBA reagent featured in this chemistry. So you can have a TEBA reagent. You can also have metallocene dialkyls. Why are these species important? Well, if you remove one of the alkyl groups on this as an anion to produce a cation, these are the species we mentioned the other day that do polymerization catalysis. So these are precursors to industrially important polymerization catalysts. So what can we do with this? Well, you can reduce this in the presence of something like magnesium or zinc and add a 2-electron donor to make new compounds. You can hydrolyze the titanium-chlorine bond, and those of you who've done either 2HO3, 2H11, or listened to Professor Botman and did the tutorials will recognize that if you hydrolyze a metal chloride, then you're likely to get a titanium or a metal oxygen metal type linker, and that kind of chemistry happens if you stoichiometrically hydrolyze these. Do I expect you to memorize this slide as it stands there? No, but I expect you to be able to recognize that these species can be reduced, and if they be reduced, they can pick up new ligands and the like. we've looked at bis cyclopentadienyl complexes. What I'd look at now are monocyclopentadienyl complexes with only one cyclopentadienyl ring. So now we don't have the wonderful stability associated with a sandwich structure. We only have one cyclopentadienyl ligand. And we often see cyclopentadienyl ligands in combination with carbon monoxide ligands, which we all know very well now. So we get into a very important class of cyclopentadienyl metal carbonyl compounds. So this one shouldn't be too difficult for you. If you take manganese pentacarbonyl chloride and react that with sodium Cp, then what you get is essentially a metathesis reaction. But if all we did was replace a chloride ligand with a cyclopentadienyl ligand, then we would easily have well over 18 electrons. So in that process, you actually have to lose some carbon monoxide. So that's what's going on here. In this case, we're producing an anionic compound by replacing 3 CO ligands with one formerly Cp minus species, and again that gives us an 18 electron compound. And what the metals there should be entirely obvious from what metal you start off with. One very important class are these dinuclear compounds. Now, if you remember, when we were dealing with metal carbonyls, can you remember which metal carbonyls gave rise to dimeric compounds? Anybody? Which metal carbonyls were dimeric? Which homoleptic metal carbonyls were dimeric? Cobalt and manganese. Right. What do cobalt and manganese have in common? One is in group 7, one is in group 9. They have an odd number of electrons in common. So where you're talking about simply metal carbonyl complexes and you have an odd number of electrons in common, then the way you get to an even number of electrons is forming a metal-metal bond. Now, a cyclopentadienyl ligand has an odd number of electrons. So a cyclopentadienyl ligand combining with a transition metal which has an even number of electrons is going to give you an odd number of electrons. So when you're dealing with monocyclopentadienyl complexes, it's those complexes with transition metals with even numbers of electrons that are going to form metal-metal bonds and dimerize in that fashion. So what we have here is cyclopentadienyl. If you reflux that up with iron pentacarbonyl, you don't have to put any other reagents in there. What you end up with is this compound here. So this is a compound which has a metal-metal bond, one terminal, one bridging carbon monoxide ligand, and one cyclopentadienyl ligand. And that is an 18 electron compound, the metal of which ought to be entirely obvious. Then, if you do it with cobalt, of course, we know that cobalt forms dicobalt octocarbonyl. This is dicobalt octocarbonyl, which has a cobalt-cobalt bond. But if you introduce a cyclopentadienyl ligand with an odd number of electrons, you don't need a metal-metal bond. And so you make a cyclopentadienyl cobalt dicarbonyl compound. And we have a couple more examples on this slide, which is superfluous to your lecture notes. What might the metals be there? Okay, so some people say the metal here is nickel. And what might the metal be here? So we know, because it's a red blob, that this is an 18 electron compound. It's amazing the courage of your convictions. I have to tell you that it rippled out from the middle. Okay. So, cyclopentadienyl carbonyl compounds are the most successful, the most common class of half sandwich compounds. And they obey the 18 electron rule. Remember how I was prepared to put my neck on the block and say, give me a transition metal and I'll show you the carbonyl. I don't have to memorize these things. I know it will obey the 18 electron rule. You can do exactly the same thing with cyclopentadienyl carbonyl compounds. So remember, metallocenes, they don't obey the electron rule. routinely, cyclopentadienyl carbonyl compounds obey the 18 electron rule. And if they have odd numbers of electrons, then they can achieve even numbers of electrons, just in the same way that our carbonyl, homoleptic carbonyl compounds did by forming metal-metal bonds. Now, what we have to remember, of course, is a cyclopentadienyl ligand is a 5-electron donor to begin with. So you can extend this chemistry somewhat earlier in the transition metal series before you have to start invoking negative charges on these species, because the cyclopentadienyl ligand is bringing that many more electrons to begin with. What can you do with these compounds? Well, this is the ubiquitous, the most famous, most significant member of the half-sandwich carbonyl complex family, CP iron dicarbonyl dimer. This CP iron dicarbonyl fragment is so ubiquitous in organometallic chemistry, it has its own abbreviation. It is called FP. So the FP fragment is CP iron dicarbonyl, which we would recognise as a radical and is normally found in combination either with another one to form this, which I guess we would call FP2, or with a halide ligand, or as an anion in these systems. So it's a 17, the FP fragment is a 17 electron fragment, needs something else to be in combination with, but it is found in combination with all sorts of things. So here's an example of this species. It does all sorts of chemistry. Remember I said that wherever there's a metal-metal bond, those species are really easily reduced. And it's just the same here. You can reduce these species very easily to make the carbonyl anions. Those can be protonated to make hydrides. Those will react with various species for insertion reactions to make alkyls. This species will react with electrophiles to do various things. And then you can do all sorts of extensive organic chemistry, which is beyond the scope of 2C32, but what I'd like you to do is just to recognise the synthetic versatility of this compound. And to summarise, I get agitated about these things. I'm a bit of a pedant for nomenclature because it is actually quite important. If you put CP for cyclopentadiene, that's not just a typo, that's a significant misunderstanding of what is meant. Cyclopentadiene has still got a proton on it. It's not the ligand that you're interested in organometallic chemistry until you remove that proton or H dot species and turn it into a ligand. CP is a pi donor and a pi acceptor. Compared to carbon monoxide, it is a better donor and a worse acceptor. So if you put a cyclopentadienyl ligand on a metal center, you will make that metal center more electron rich, which has all the consequences that we've discussed so far. 18 electron rule is brilliant for these half-sandwich compounds, but it isn't rigorously obeyed for metallocenes, because in the metallocene, the sandwich structure itself is an island of organometallic stability. The most stable compound occurs where they both coincide together, but you can get metallocenes which have 17 or 19 electrons as well. You can predict how they're going to react by either gaining or losing an electron based on the 18 electron rule, but you can't say they won't exist, they won't be stable. They are, and they do. Okay, so that summarises this. After Easter, Easter comes at a sort of, well, it never comes at a good time if it breaks up the term.